Hello everyone, and welcome to Session 1 of the Shimadzu Introduction to Liquid Chromatography series. This series of webinars is designed to introduce and increase your knowledge within this area. This first session in the series is looking at the fundamentals of liquid chromatography. My name is Angela Jean and I will be your presenter today. I am part of the LC technical team at Shimadzu within the UK. Before we start today's content, I would like to introduce the LC technical team for Shimadzu within the UK. Firstly, we have Raymond Wong, who is the LC product manager, and my colleagues Earl McCoy and Richard Hodson, and finally myself, Angela Jean. I will be giving today's webinar, and you will hear from the rest of the team throughout this series and during future LC webinars. The Shimadzu Introduction to Liquid Chromatography series will consist of multiple sessions. The first, today's, is titled Fundamentals of Liquid Chromatography. This topic will include what is chromatography and what is liquid chromatography, what does an LC column do, what types of samples can we analyse, and what makes up an LC instrument. Our next session will concentrate on the most common types of liquid chromatography separation and what affects those separations. Future sessions will cover topics such as common issues, tips and tricks, building your method and developing it, optimising your method and your instrument, and troubleshooting common issues in both your methods and your datas. So let's begin with the content of the first session, Fundamentals of Liquid Chromatography. What is chromatography? The definition of chromatography is a technique for separating a mixture of substances. All forms of chromatography have a mobile phase that transports the mixture across a stationary phase. As substances are different in their properties, they will interact with the stationary phase or the mobile phase differently. This difference in interaction alters the time it takes to travel across the stationary phase. We can see this clearly using a form of chromatography called paper chromatography. In this example, our stationary phase is paper. Our mobile phase is water placed at the bottom of a vessel. As with all paper, the water will slowly travel up. We then added various inks 1, 2 and 3. These are primary colour inks and therefore will only separate into the single colours. We also have mixes 1 and 2. These are combinations of various colours and are also known as unseparated mixtures. So as the water absorbs up the paper, our inks and mixtures will also travel up the paper. The rate of travel will depend on the interactions between our water mobile phase and our paper stationary phase, as well as the ink themselves. As the mixtures travel, they will begin to separate into their individual components. These individual components travel at the same rate as the individual inks. Our result is that our mixtures are now separated into their individual components, with mixture 1 now separating into its yellow and blue inks. Having looked at what chromatography is and how it works, we can now look at the 4 main types of chromatography. We have paper chromatography, as described with our ink separation. We then have thin layer chromatography. This utilises a thin layer of silica, replacing the stationary phase of the paper from our paper chromatography. Gas chromatography. Please visit the Shimadzu UK website for links on webinars on the fundamentals of gas chromatography should you wish to know more about the fundamentals and basics of gas chromatography. Finally, liquid chromatography, which is the topic of today's and future sessions. So what is liquid chromatography and how does it differ to our paper chromatography example? Well, liquid chromatography still uses a mobile phase and a stationary phase. The paper stationary phase is now replaced by a column packed with particles. The separation is still achieved by the compound's varying attractions of the mobile and stationary phase. So what do we mean by attraction to mobile and stationary phase? Well, let's use a visualisation of a shopping trip. We can take a shopping trip with multiple shops. Here, our mobile phase, represented in red, will travel throughout the shops constantly. Our compounds, or shoppers, require different items. Our square, it requires a limited number of shops in order to pick up their items. Whereas our donut needs an awful lot of items and will require to visit multiple shops along the way. With our shoppers shopping at different numbers of stores, there is time to separate between the two of them, with our mobile phase continually going throughout all the stores. So having looked at our shoppers along a high street, we need to now look at this in terms of the liquid chromatography column. HPLC columns are packed with small particles, but they are always plumbed into the instrument in a certain direction to allow the flow through the column. This is always indicated on the outside of the column. The inside of the column is packed with particles, most commonly silica. These particles in modern columns are spherical and uniform. The diameter of these particles is represented within the numbers on the outside of the column. The inside of these particles is like a network of pathways, similar to the structure of honeycomb. Along the outside of the particles, as well as the walls of the pathways, are compounds known as functional groups. These functional groups create an environment that promotes interaction of the compounds, enabling separation. These functional groups are represented in the column types, such as C18 or phenyl hexyl. Our choice here is a C18 functional group. This will differ in its functionality from a phenyl hexyl for different compounds. So knowing the compounds of analysis is vital. The functional groups here, C18, will allow the interaction or lack of interaction of the chemicals and compounds as they pass by. It's all dependent on the nature of your compounds, the same as we saw with our inks. So we can now revisit our shopping trip, relating this to an LC column. Here we have the LC column with the silica particles and our functional groups of the C18. A C18 is an 18 long length carbon chain which is attached to the silica bed. We have a mixture of compounds that will interact differently with the functional group of the column. This in turn creates a response from our detector, creating a chromatogram based on when it sees our compounds. First red, then green, then blue. So we mentioned a chromatogram. So what is a chromatogram? No matter what type of chromatography we are using, the output is known as a chromatogram. The word chromatogram is defined as a visible record of the separation of components in a mixture. In liquid chromatography, this separation occurs whilst travelling through the column. The chromatogram is then the response that our detector provides us, which produces a spectra such as this one, as it sees the different components coming out with time. So what information can we obtain from a chromatogram? Well, we can use the x-axis to calculate the time the components were retained from being injected to being seen by our detector. The peaks represent each different compound within our mixture. Also represented is the baseline, which is our background signal from our mobile phase. The time our peaks are seen by our detector is called the retention time, and this is relative to time zero, the time the mixture or sample was injected. The area between our baseline and the top of our peak is used most commonly to determine how much compound is present within a mixture. We have looked at how our compounds separate, but what types of compounds can we analyse? Firstly, they must be soluble in your mobile phase. If they are not soluble, then instead of a liquid moving through the column, small particles will begin to drop out of solution, and these will block those narrow pathways within the column. We can analyse a wide range of molecular weights, from very small to large biomolecules. While most liquid chromatography is done on organic compounds, it is possible to look at inorganic compounds using the right conditions. The compounds must have some interaction with the stationary phase. This will create the separation. With no interaction, this will lead to no separation, all based on the type of separation we are trying to achieve. So we now have a list of things we can analyse with an LC. However, please note that we cannot analyse compounds that are gas at room temperatures. These volatile compounds are better suited to gas chromatography. Please see our webinar series for gas chromatography for further information. We also cannot analyse compounds that are similar to our choice of mobile phase. The interactions with the stationary phase would be too similar and would therefore not allow us to see a difference in signal between the compound and mobile phase when it reaches the detector. We now know the major types of compounds we can and can't analyse for. As the mobile phase aids the interaction with the stationary phase, what must or should your mobile phase contain? As we said previously, the mobile phase must solubilise your mixture. If we are combining different solvents, then these solvents must be miscible with each other. If they are not miscible, then they will separate whilst going through our HPLC column, and the process of separation will not work correctly. The solvent must promote interaction. Sometimes a simple change from one solvent to a second solvent can alter that interactions enough to separate two compounds within our mixtures. We may require pH control. This is a valuable asset if you have compounds that ionise easily. The control or adjustment of the mobile phase's pH will allow for the correct mobile phase environment to promote your compound's interactions with our column and thus separate. Solvents must not mask your compounds. This can happen in a couple of ways. Firstly, your solvent could change your original mixture. This could be through some process such as degradation or binding. This changes the compound that you were looking at, and thus the detection will not be of the original compound but of your degradation products or bound compound. Compounds that are seen at low wavelengths require a solvent that will allow them to be seen. What do we mean by this? looking at solvents for uses within mobile phase and their various UV properties. This is known as the solvent cutoff wavelength. Here is a table of commonly used HPLC solvents and their relative UV cutoff wavelength. This is a wavelength at which they would block the signal of anything needed to be analysed underneath this wavelength. For instance, the sample of hexane has a cutoff of 200 nanometers. Any sample below this would not be seen. So a compound that we need to analyse at 215 nanometers could not use any solvents from diethyl ether onwards, as these would prohibit the detector seeing our compound. We now know how the column separates our mixtures, but what about the instrument as a whole? Well, we start with solvents, as we've spoken about, our mobile phase. We have a pumping system that passes these solvents throughout the whole instrument. We'll have an injector system that introduces our mixtures. We have our column, which allows us to separate these mixtures into individual components. And we have our detector that will see these individual components once separated. These are all connected with tubing to complete our instrument. So no matter if the instrument is made up of individual modules or they're housed in a single unit, known as integrated, the formation of the LC will be the same. The solvent will be drawn into the pump, and on its way through towards the column, our sample will be injected. This sample will then travel towards the start of the column, where it will begin its separation journey along the column. From here, it will pass quickly towards our detector, producing a chromatogram at the end. As we've just mentioned, there are two types of LC instruments, a modular or an integrated version. Each type contains the same sections and works in the same way. The major sections are mobile phase, pumping system, a degasser to remove any excess gas from our mobile phase in order to protect our column, injectors to introduce our mixtures, column ovens to ensure that our whole column is within the same temperature environment. This promotes equal and consistent interactions with the column and our compounds. And finally, detectors, which are available in various types and ensure that our different types of compounds can be seen once they have been separated. As you can see, all sections are present within both types of instrument, both modular and integrated. With our knowledge of what compounds can be analysed, what type of industries do you think use liquid chromatography? Here are some examples. Agrochemical. The agrochemical industry produces products that are used on crops and plants, both within industrial fields and within our own back gardens. Pharmaceuticals. This could be analysis of our raw materials or even our final products at any stage within the drug and herbal remedy industries. Within the industrial sector, analysis of compounds such as paint, inks, textile dyes, or even plastics and cosmetics can be carried out. Within medicinal and veterinary areas, clinical trial samples can be analysed, veterinary drugs, or even human tissues such as blood, urine, or tissue analysis. Within the environmental industry, it is essential to test soil, water, and even waste streams. Within the food and drink industry, all types of testing is carried out to ensure that quality across products is attained. So in summary of today's session, liquid chromatography is a common technique for analysing mixtures of various types of compounds. It is suited to analysing a large range of molecular weight compounds, utilising their varying individual chemistries to aid separation. LCs separate using the various solvents of our mobile phases and utilising a column that is packed with particles, creating our stationary phase. An LC instrument comprises of mobile phase, a pumping system to push the mobile phase around our instrument, an injector to introduce the sample onto the column itself to perform the separation, a column oven to control the separation and elution of compounds consistently, and a detector to detect the eluting components and produce our chromatograms. If you found today's webinar interesting or informative, please do join us next time. Session 2 of this series will be conducted on the types of liquid chromatography and using separation techniques. This will cover the most common types of liquid chromatography, how the techniques work, and what affects the LC separation. Please visit our website www.shimadzu.co.uk/webinars for other webinar sessions that are open for registration or available on demand. If you'd like to hear more from Shimadzu, please do join our mailing list. You will receive all the news and product development from us. Look for the link on the follow-up email or go to www.shimadzu.co.uk and click on e-news located at the top of the screen. You can find us on all the usual social media platforms. Please feel free to contact us should you wish to find out more. That's all from me today. Thank you very much for participating, and please enjoy the rest of your day.
Excellence in science. Shimadzu.